Recurrent neural networks, or short RNNs, are an essential part in deep learning. They are widely used and are incredibly effective in many different kinds of applications, especially in the field of natural language processing, like for text generation or text classification, but they can also be used when working with images or video data. So in this video we learn what RNNs are and how they work. This video is part of the Deep Learning Explained series by Assembly AI, which is a company that creates a state-of-the-art speech-to-text API. And if you want to try their API for free, then grab your free API token using the link in the description below. And now let's get started. First, let's have a quick look at one definition of RNNs. RNNs are a special class of neural networks that operate on sequence data and allow previous outputs to be used as inputs while having hidden states. So let us reiterate. They are also neural networks. They have something to do with hidden states, and they can keep track of previous outputs in a sequence. So if this definition is not clear for you right now, don't worry, we will come back to this in a moment. But first, let's have a look at why RNNs work so great. And for this, we look at one example. Let's do a quick test and complete this sentence. The color of the sky is blue. Or another one, I grew up in Germany, that's why I'm fluent in German. And I bet you guessed the correct word, because for our brains it should not be a problem to determine the missing word. And we know the word because we know the previous text. We don't just look at one word and throw away the previous information. We remember the previous context and then use this information. And this is exactly what RNNs do. So if we try to do this word prediction with a normal neural net, then this would not work, because one major shortcoming of neural nets is that they cannot keep track of previous outputs. And this is what RNNs try to fix. Now let's go back to the original definition. By now it should be more clear what is meant with sequence data and previous outputs. For example, a sequence data can be a sentence where the RNN looks at each word separately, encodes it to a mathematical representation, and can then remember the previous outputs. But how exactly does this work, and what are these hidden states? So a normal neural net gets an input, then has different hidden layers and returns an output. Now RNNs have loops in them, allowing the information to persist. So we can also unroll this loop and look at this picture in a different way. We can now interpret this as a sequence data with different time steps. We have the first input where we do calculations in the hidden layers and can then get an output. And then we pass the information from the hidden states onto the second time step. And here again we get an input, then we do calculations where we now can use the previous information, and then again can get an output and pass on the information, and so on. Now each time step contains the information from all previous steps, so the last step has information about all the previous context. And then, for example, we can use this very last output here and pass it on to a simple linear classification layer and do the word prediction like in the example from before. So by now I hope the explanation and motivation of RNNs is clear to you. Another reason why RNNs are so powerful is because of their flexibility. Now, normal neural nets or convolutional nets have the limitation that they don't remember previous states. And moreover, they accept a fixed size vector as an input and produce a fixed sized vector as an output. For example, one image can be the input and the probability of different classes is the output. So this is what we get with traditional neural networks, and recurrent neural nets, on the other hand, operate on sequence data. So they operate over a sequence of vectors. And this could be sequences in the input, the output, or in both. And this allows for many different applications. For example, we can have a one-to-many relationship, which can be used for music generation. So we get one input, but many outputs. We can also have a many-to-one relationship. So we have many inputs, but only one output. This is, for example, used for sentiment classification. And we can have different types of many-to-many relationships. For example, here for name entity recognition or for machine translation. And by the way, these images are taken from the Recurrent Neural Networks cheat sheet that you can find on the official Stanford website. And I will put the link in the description for you. Now, how do RNNs learn? And basically the same as other neural nets, they learn by the backpropagation algorithm, and to be more specific, by backpropagation through time. So we do a full forward pass through all the time steps, and then a full backward pass through the entire sequence and calculate the gradients. So nothing really special here. And by the way, if you want to learn more about backpropagation in detail, then we have another video for you on our channel that we link here. Now, this long way of traveling can have one major problem. The more layers we have to travel through, the more multiplicative gradient calculations we have. And this can lead to a so-called vanishing gradient or also to an exploding gradient. And this in turn means that these information get lost and it gets difficult to capture long-term dependencies. So the more time steps we have, the less information we can keep from time steps that are further in the past. So let's again have a look at the two sentences from the beginning. The color of the sky is blue, and I grew up in Germany, that's why I'm fluent in German. In the first example, the relevant information are sky and blue, so they are close together. But in the second one, maybe we can guess the word should be a language because we see the word fluent. But to guess the correct language, we also have to read the previous sentence. So we have to go further back in time. So the more we have to go back, the more difficult it can be for our RNN because of this problem with the vanishing gradients. But luckily, there are existing solutions that tackle exactly this problem. Long short-term memory, or LSTM, and gated recurrent units, or GRUs, are two special variants of RNNs. They are capable of learning long-term dependencies using a mechanism called gates. So they often outperform simple RNNs and are important to know, but getting into more detail here would be too much for this video, but I'm sure we will cover them in a later video in the series. But also having these two improvements does not mean that simple RNNs can be skipped, because on the downside they are computationally much more expensive, so in many cases a simple RNN will be just fine. Now at the end I also want to quickly show you how you can use this in code. So both deep learning frameworks PyTorch and TensorFlow make this pretty easy for you because they have existing layers that you can use. For example, here is the PyTorch code. So here you can set up this RNN layer and you find this in the torch.nn module. And the same way you will also find the LSTM and the GRU layer. And then what is important to note is that when we call this layer in our forward pass, we also have to put in a hidden state. So here we initialize the hidden states with a zeros tensor, and then we pass it to our RNN layer. And then we get two things back. One is the output and one are the encoded hidden states. So yeah, this is how it works in PyTorch, and in TensorFlow the API looks different. But here again, you have the layers already available. For example, you can use the simple RNN, or also LSTM and GRU are available. And then you can put this in a, for example, a sequential model. All right, I hope I could explain RNNs in a simple way. If you still have questions, then let me know in the comments. If you enjoyed the video, then please leave us a thumbs up and consider subscribing to our channel. And then I can recommend to watch this video if you haven't already about backpropagation. And then I hope to see you next time. Bye.